Good afternoon, everyone, and welcome to another ABC Tab Talk webinar. I'm Sam Schwartz, and I'm going to be your moderator today for the webinar. Thanks to all of our members and for those non-members on there across the community for participating today. And a special thanks to Evergreen Telemetry for supporting this webinar. I'm going to cover a few housekeeping notes before we jump into things. If you have questions for our speakers, please use the Q&A button in your Zoom window, not the chat box, and we will feed those questions to our speakers at the conclusion of the presentation. You can submit questions at any time, though, so no need to wait until the end. If you have technical issues, please use the chat box to inform the panelists, and we will assist you. And then finally, concerning AIA Learning Units, if you are an AABC certified TBE or TBT, please allow 7 days for your CEUs to be uploaded automatically to your portal. Today's session topic is airflow measurement and control with induction diffuser technology. And joining us is Todd Yates from Synergy Test and Balance. Todd is a mechanical engineer licensed in Kentucky and other states. He began his career in test and balance in 1991, developing a specialty in complex HVAC systems used in healthcare, research, laboratory facilities as well. After leaving the tab industry for a time to focus on building commissioning, he's re-engaged in test and balance in 2011, continuing to maintain his expertise in complex HVAC and building control systems. So now that we have everything started, I've introduced Todd. I'm going to hand it off to him to take it away. Todd?
Thank you. So the description of the course today is airflow measurement and control with induction diffuser technology. A little bit about this building. It's a multi-floor university project with central air handlers serving VAVs tied to induction diffusers. Because the airflow and induction diffusers cannot be measured directly with a flow hood, they have to be measured with another method, primarily the drop at the factory installed ports. The initial work on this project with traversing these units were significantly different than the induction diffuser readings, and resolving this conflict took quite a bit of time and input from several people, and I want to walk you through the process of this system, how it works, and how we got these issues resolved. Our learning objectives will be to explain the operating principles of induction diffusers, review the balancing procedures for induction diffusers, discuss effective coordination between the project stakeholders on technical issues and expectations, examine the alternate measurement methods that are possible with these systems. And we will use this agenda. We'll start with what is an induction diffuser. So these are made by different companies, but the brand, and from our research, one of the main brands that build these is this company, Danco. And this is their definition of what they call their infusers. They're an induction diffuser that use specialized nozzles to draw in plenum air or room air in some cases, mixed with the primary air from the air handler. And this is mixed before it's discharged into the occupied space. So what is the difference between aspiration and induction? Aspiration is the technology that we see in all ceiling diffusers, virtually all of them that we've looked at, that we use, see in our day-to-day tab life. And you can see at the bottom of the screen here at this graphic, aspiration is shown in orange, and as the air is ejected from the diffuser, it draws room air into it and gets mixed before it goes to the occupants of the space. You don't really want 55-degree air hitting the occupants. That's going to cause comfort issues and complaints. So this aspiration effect is typical of what we see in normal diffuser technology, and it's part of induction diffusers as well, but they add a different component to that. So with induction, it mixes room air or plenum air into the airstream before it's discharged into the occupied space. So you can see in this graphic below, the primary air is ducted into the diffuser that's coming from the air handler. It works through these nozzles down into the infuser itself, and that draws in the secondary air. That air is then mixed and ejected into the room, at which point it's mixed with more room air through the normal aspiration process. So here's a graphic that shows how this works. You can see the airflow patterns, how it goes into the diffuser. And this one is the type of technology that we had on ours, where, and we'll get to more detail about the types of where the air from the room is entrained through the center of the diffuser. It's mixed with the primary air from the air handler and then ejected into the space. And the primary air ratio is entrained. Typically it ranges from 1-to-1 up to even 2-to-1. They varied some on this project, but for the most part, they were in the 1-to-1 range. So if you had 50 CFM of primary air, you could expect the design to be 100 CFM of mixed air coming into the space. That's what would get the air to the occupant level. But that's not the primary thing we're interested in, because that's not what we're balancing or even measuring, but it affects how we do those things. So there are two types of entrainment. External entrainment is shown as this in this graphic. The blue line, number 1, shows air coming from the air handler coming into the diffuser, and it's mixing with plenum air. That's the red arrow. These two air streams are mixed together and go into the room in the green arrows labeled 4. So this is not the type that we had, but this is, you may see these, so I wanted to be sure we included some introduction to that type as well. The second type is called internal entrainment, and this is what we had on our project. So we had air coming from the air handler in number 1, the plenum box and all of the infuser was above the ceiling. All you could see from below the ceiling was what looked like a typical diffuser, but it's drawing air through the center in the red airstream number 4 and being discharged, mixed and discharged into the space with the green arrow number 5. So what are the applications and benefits? Why would we use these things in the first place? And this was the first time we had seen these. As a matter of fact, the project is still ongoing. It's a multi-phase project, and it's still the only time we've seen these. Though usually when a technology comes into a region, sometimes it's the first time is literally just the first time. So we do expect to see more of these. We'll talk about why. These are used where increased air circulation in the occupied space is desired due to a high cooling or high heating load, potentially high ceilings. What you get is a greater velocity at the diffuser than you would get just from the primary air from the air handler. So that creates better mixing, better airflow within the space. It can also be used in tight spaces where smaller primary air ductwork must be used. And that's what we had in this project. It was an existing building with very limited space between ceiling and deck, and there literally was not enough room for ductwork sized to handle the amount of air that would be required with the traditional VAV system. Spaces where drafts are problematic is a third reason you might use these. And because it's entraining the air from the space mixing with the primary air, even though you still have the same cooling load that you might have, but because drafts are an issue in these areas, the air is warmer, closer to your design room temperature by the time it gets to the occupant level. These are also used where quiet operation is required. to occupied space if noise levels are a concern. And in some instances, they can be used to replace fan-powered VAVs because they do, they can mix that plenum air before it gets to the occupant areas. So, how do these things? One of the points is that they can save energy. Well, how do they do that? They do that primarily through fan energy because they don't change the cooling load in the space, but because you're using less primary air at a colder temperature in smaller ductwork, you need less fan energy. So this is a chart of showing energy savings with induction diffusers. And the greater difference that you have between your primary air and your traditional primary air and what you're lowering that primary air to, that defines the savings. So this one, let's look. So if we have a 20-degree initial difference and we have a 6-degree change. So let's say your space was anticipated to be at 75. Your primary air would have been at 25. You're now going to lower that 6 degrees, or I think your primary air would be at 55. You're going to lower that 6 degrees. So you take the initial delta T, follow that up to your change line, and then follow that to the left. So in this case, we had a 23% reduction in primary air over a conventional VAV system. So that 23% reduction in primary air is about a 54% reduction in fan brake horsepower. So there's savings in operating costs, and there's also upfront savings because you're using smaller air handlers. We realize that savings, may come with a cost, and we're not espousing these as the answer to every solution or the answer to every problem, but it is what the designer chose in this case to deal with the limited ceiling space they had. So one thing that these did remind us of, and it's instructive, I think, to talk about this is chilled beams, because the same company makes chilled beams and uses some of the same technology. And we've balanced a lot of chilled beam projects, so that informs us a little bit about how these work and what we can and can't do with these. So a comparison to chilled beams, they all provide increased air movement without increased primary airflow because they're inducing air into the device. They require smaller primary air ductwork compared to a traditional VAV. They use the same nozzle technology to induce that airflow. One difference is these induction diffusers do not add any additional heating or cooling capacity. They're passive in that sense. They're an airflow device only. There's no water, no coils connected to them. However, they're similar in that airflow cannot be measured with a flow hood. So what are the balancing procedures for this? So coming from the manufacturer, they tell you do not attempt to confirm total supply airflow with the traditional flow hood. And they explain that with the low velocity of the air, the low pressure in the airstream, so just the number I used earlier, if you had 50 CFM of primary air, and that was going to be mixed with 50 CFM of room air to deliver a total of 100 to the occupied space. If you put a flow hood on that, you'd immediately cut out the 50 CFM of induced air. But what they're saying is that you would also, the back pressure would prevent the 50 CFM of primary air that would normally flow. The hood itself would impose a restriction that would cause that to change. Therefore, your reading would be inaccurate. So the second method they tell you to avoid is a duct traverse. And they explain that due to low flow, that pitot tube traverses don't work well. Low velocities and boundary layer measurements cause inaccuracies that prevent this from being useful. And we did read that, we did see it, and at the end we understood better why that came to be. But let's walk through a few more items here and understand how these devices work and how to balance them. So with their procedures, They've told you what to avoid, what not to do. Here's how they recommend doing it. So they provide charts and CVs, and this is consistent with all manufacturers of these devices. But this chart is from the infusers that were on our project, and you can see there's 4 different nozzles available, and they fit these nozzle arrays to the diffuser based on a number of things, and specifically, how big it is, how much airflow, how much primary airflow, and how much mixed airflow that you're going to need. So you can see in this is a cutaway of the technology. So what we want to measure is this blue arrow coming into the top of the diffuser. And the way we do that, according to the manufacturer's instruction, is to attach a manometer of some sort. I think we're all using electronic manometers these days, but to attach that at port labeled number 2 in this drawing, and the other port is going to be open to the space. And notice with this type that you're always going to have to be above the ceiling to get to this. I know some chilled beams have ports that are accessible through the face. You don't have to remove a ceiling panel with these induction diffusers. You do have to be above the ceiling to connect to port number 2, and then your other port is open to the space in the room. So now this is from the submittal on this project, and it's a good deal more detailed than the graphic. The graphic shows you what's going on, but if you really want to calculate these, then this is how you would do it. And I did like the design, at least of the the documentation they provided, because these are very precise. And on this project, every infuser had a specific airflow rate, and that airflow rate was consistent wherever you saw it. Take an IN-4, for example. Anywhere that appears on the drawings, that is to get, and you can follow that line across. An induction diffuser number 4 is to get 70 CFM of primary air. And more importantly, in this primary air, just before the yellow bar there, you see the primary air pressure. So you should, at that port I just showed you, if you had exactly 70 CFM of primary air, you would have 0.116 inches of pressure drop there. So that's, you can calculate a CV for that. One of the things that we did is create a small spreadsheet for a technician on this project so that they could take a reading, put their differential pressure in a box, and they would get the airflow immediately. So they would know what to record for that one, rather than doing trying to do complex calculations in the field. Even if it's repetitive and simple, that was a tool that we created for this project just to simplify their work in the field. So the traditional method of balancing a VAV with ceiling diffusers is roughly this, and I think this is what we would all do in a typical office, classroom, building type setting. You would override the VAV to its max CFM setting, measure the airflow at all the ceiling diffusers using a flow hood, and then you would calibrate this VAV with the sum of that diffuser airflow. Once that was done and the VAVs settled out again at its maximum, you would proportion the diffusers using the manual balancing dampers. At that point, you would measure and record final diffuser airflow. So our initial approach to this was similar. We knew that we couldn't read them with hoods, but we also thought that climbing into the ceiling, because some units had as few as 1 or 2 induction diffusers, some had as many as 10. So we thought that it's going to be a bit tedious to have to take 10 differential pressures, move around, move the ladder. It's not like you can just walk through with a hood and measure each of these. You've got to move a ladder to each one. You've got to climb up, take the differential pressure. And even if you're doing what we did and putting that in a spreadsheet to make it simpler, it still takes a lot more time. So this was our initial approach. We thought, Well, if we can override the VAV to maximum like always, and then use a duct traverse to calibrate the VAV, then we know that our VAV flow is accurate. And then we can measure the flow at each induction diffuser with the differential pressure, but we wouldn't have to measure them all first. We could go to the first one, and if it was high, we could cut it down. We could proportion the diffusers with just basically one trip through without having to make that additional trip through all the diffusers. And then, of course, at the end, we would measure and record the final diffuser airflow. So this was our thought process that we would, we would streamline this a bit. So let's look at what happened. We had a significant airflow difference, compared to the duct traverse. And this is just one of the VAVs. Had 3 induction diffusers. We traversed 387 CFM, but the sum of our induction diffusers using the prescribed method of the induction, the pressure drop, and calculating that using their submittal, we came up with 299 CFM. So the induction diffuser total was 77% of the duct traverse. So that was a little concerning. We tried a few others. That we had again, here's another sample. Again, different box, 3 diffusers, 659 CFM on the traverse, 485 CFM with the sum of the induction diffusers, which is 73.6%. So we looked at all things. We looked at is there duct leakage? Is there an access door on the VAV leaking? Is it leaking at the connection to the reheat coil? What's going on? We couldn't find any of the typical installation problems that we might have guessed there. So then we tried testing it with an individual diffuser. We said, well, what if we try one of these? It's not working when we're summing them. Can we try it on just one? And we know you can't always get a good traverse on an individual diffuser, but we found a few where we had good enough duct runs to take a duct traverse. So here's one off of VAV 12 serving an office, 114 CFM traverse, 97 CFM from the DP calculation, and wasn't as bad as some of the totals, but still 85%. That's too big a difference. That's not going to work when you think of if you have that kind of error over the whole system. That's just not going to be acceptable. So we kept looking. We tried another one with similar results, 194 CFM on the duct traverse and 161 CFM on the DP calculation. So we put this into a table to try to understand a little better, try to get our mind around what was going on. We submitted this information for others to review. We tested 8 VAVs total. We tested 4 individual diffusers from those VAVs to try to see if we could narrow it down and find some case that that showed us what was happening. So there's a lot of data represented here. We're not going to go through all of that, but I wanted you to see the process that we used and the kind of things we looked at as we were trying to sort this out. So we sent this information to our client. We requested a meeting. We said, we're not quite sure what's going on here. And as any project is, it's under time constraints. You have to meet the deadlines for turnover. And so we said, we can't do that without some assistance. So we had a meeting with the owner, the designer, the mechanical contractor, the equipment manufacturer, and us. Well, the manufacturer insisted that the DP method was accurate and correct. He didn't really give us any other information about having run into this problem on similar projects, just that their literature was correct and this is what we should do, and that was the only way it would work. The mechanical contractor contacted a second tab firm in another state that they'd worked with quite a bit, and this fellow said that yes, we've seen this. We've done a lot of these projects, and these things are almost never accurate. And what we do is we traverse one, we'll traverse a couple of the same size, and we come up with a new CV. And back to that chart I showed you earlier from the submittal, you can take that. If you know at 70 CFM, this is the pressure drop. If you know what that is, you can calculate a CV. And so that's what this test balance firm said that they did, is they calculated new CVs and used that to complete their balance. And the designer liked that, and he initially directed us to proceed with that approach, essentially creating a new CV or a correction factor, whichever way you want to name that. But then he reversed course, and the final direction was for us to use the induction diffuser DP. So we knew that we could do that, but still, being the sort of kid that like to take his toys apart to see how they worked, I had to understand why it was doing what it was doing. So back to this approach here, these tables I showed earlier. We started looking at this a little closer, and for the purposes of this presentation, I trimmed out some of that information so that you could see it better. Some of the things that didn't, ultimately didn't play a factor. And I got it down to, just looking at these, the VAVs, the duct traverse data, the outlet total from the induction diffuser DPs, the difference. And I even included the number of induction diffusers in case there was any correlation there. Turns out there wasn't, but we didn't want to exclude anything that we thought, might be important. So if you'll notice in this in that table, there was one that was different. I'll go back to it just for a second. VAV 13. Notice that the difference in the percent of ID total versus VAV traverse column, that it's 98.7%. Those two readings were almost exact. And so we started looking at that one to see, why is it different? So our traverse was 389 CFM. The sum of our induction diffusers was 384 CFM, virtually exact. You could take the same reading twice and come up with more difference than that. So, why is that? What's different about this one? Well, when you put it in here and you highlight that single bar and compare to the others, the thing that sticks out immediately is the test velocity in the traverse, and it's very high compared to all the others. And while I know that you can't, if you're using a liquid manometer, for example, or to take a duct traverse, I know that you can't average your velocity pressures. But just for the sake of picturing what was going on, we said, well, what if every traverse point's exactly the same? What would the velocity pressure be for this average velocity? And you see that it's 0.236, where some of these others that were well away, where we had big differences, are down 0.01, 0.013, 0.009 for one of them. Those velocity pressures are very small. So we started looking to see, is there anything published anywhere that tells us any more about this? And we went back to our AABC books. What does our standard say? And I know that there's a lot of information in the standards, and I know we're not consulting it every day. But here was a problem we had to solve, and we started looking to find out, can we find some direction there? Well, the one thing that I found in the current AABC standards was a section on flow factors for measuring airflow at devices. It wasn't exactly what I was looking for, but it was the only thing that I could find that addressed the problem. And it says, to avoid low flow errors, it is recommended that traverse average velocities be above 1,000 feet per minute. And you'll see in that table that only two were above 1,000, and the one that was closer to 2000 was the one that was accurate. Let me go back to that. So we had we had some very low velocities here, 400, 500 in that range. We had the one at almost 2000 that was very accurate. And then we had the one that was at 1130. You would have expected maybe a little more accuracy from that one if that was the issue, but it was a little better, but didn't really prove the case to us entirely. So we went back and we started looking at that to see, is this really where it is? So we did some more testing, and we started looking at the instrumentation. We said, well, what might that tell us? And this is from Shortridge, but other we have other brands that we use that our technicians are supplied with, and we've looked at others at the the various ABC events, and so we compared all the information, but Shortridge has this nice table with all the information in one place. It was easy to get to, so we started looking at that to see if that could explain it. So as I said, similar to other brands, and even though the air velocity, also really the two things that matter to us here are air velocity and differential pressure. So the air velocity is plus or minus 3%, plus or minus 7 feet per minute, from 50 to 8,000 feet per minute. So that's a pretty big range. The differential pressure, though, was interesting as well, because it's plus or minus 2%, plus or minus 1/1000th of an inch water column from 0.05 to 50 inches. And the important thing to note here is that the low end value that they give us is 0.05. And then we all know that we can expect additional issues from field conditions. These are what they see in the laboratory. These are what they can reproduce under laboratory conditions. And field conditions are always going to cause us more issues, problems, and cause accuracy to suffer. So dialing in on this a little bit, I want to focus on the differential pressure, and you can do what I'm about to go through using air velocity, using their percentages and feet per minute offset there, and come up with something similar. But I just kind of I focused on differential pressure because that's the thing you're actually measuring, whether it's with a pitot tube or Velgrid or whatever. That's what you're measuring. That's what you're going to see. So I took this and I said, this table would come out a little differently if I use the air velocity, but I use the differential pressure. Some of these are a little higher, some of these are a little lower if you go the other way, but it still shows the pattern that we saw in our field work. So at a velocity of 2,000 feet per minute with a standard pitot tube, your velocity pressure would be 0.2494 inches. And I said, well, what if I took the high air and the low air on that? If I said I'm going to add 2%, and then I'm going to add another 1,000th of an inch, so that should be the high end velocity error. And I did the same thing for the low end. I subtracted 3%, and then I subtracted another 1,000th of an inch, and that's how I came up with the high and low error just on velocity pressure. Then I took those, turned them to velocity, and see where I land. And actually, if you use the air velocity in these higher velocities, these come up a little bit. Some of the lower ones drop a little bit, but the trend is the same. Higher velocity is more accurate to a point, obviously. So we've color coded this just to show you, where the problems seem to take off for us. And the 8 that I'm showing in here is just the 8 that we had supplied when we were initially solving the problem. Through the course of the project, we checked a lot of others to confirm that we were seeing, what we were seeing was consistent, and it was. So I didn't include that data in this presentation. It just becomes too jumbled on the screen. But so we're seeing, things when you're above 900 or 1,000, your error is really pretty low. When you get down to 800, you're getting into a range where that area is beginning to increase 2, 3, 4%. You get down close to 500 and below, then your error is really getting large, and down at very low rates. You would have to be below, well below actually, where Shortridge says that they can read, because they tell you their differential pressure readings are plus or minus 2%, plus or minus 1,000th from 0.05. And you can see that 0.05 starts just about, it would be just below 900. So it makes that 1,000 feet per minute reminder from the ABC standards, makes you really see where that, where that came from, and why that's a practical solution, something we should be looking at on our projects. So we took a couple of these, and you can look at these VAV12 and VAV13. Now these are almost identical VAVs. There's 10 CFM. I think one is a 380 CFM design, and the other one's 390. So virtually no difference there, except one of them has this 10-inch round transitioning down to a 6-inch round at the VAV. The other one is a 6-inch round from the main all the way to the VAV. So that was our traverse point. So in a way, we stumbled into this. We didn't even understand at first, why we were seeing it. We just, these were the VAVs we started on. We wanted a large enough sample to prove what was happening, and we managed to get this VAV 13 in there that had this difference. But so, when we go down to these, each had 3 diffusers. The diffusers were similar. The total flow was similar. Everything was similar on these 2 boxes, except for the size of the duct feeding it. So when you take this same snapshot where I'd pared a lot of information down, you can see that all of the low velocity traverses were inaccurate. We had low velocity 400, 300, and look at those velocity pressures. Think about that. We don't normally think in terms of velocity pressure with a pitot tube, because we're using devices that calculate that for us. So we don't have to think in those terms. But those velocities are all the velocity, the associated velocity pressure is well below the 0.05 that Shortridge says that's the low end of where they're, not the low end of what they'll read, but it's the low end of the scale they give you for accuracy. And then we had only 2 in this set, VAV09 and VAV13, that were above that pressure. 9 was barely above it, but it had the added complexity of having 10 induction diffusers. So maybe that was some of the reason that we still had a fairly high error on that one. But 13 was just lovely with virtually identical readings. So at this point, we knew that we were at the solution of the problem. So that's how we continued. So we balanced the rest of the. As I said, this is a large facility, multi-phase. This was the first phase of it. So we balanced the rest of them using the methodology prescribed by the manufacturer. We measured the differential pressures, and then when we were done with that area as a confirmation, we could dump these VAVs and get a total flow that we'd calibrated with using the differential pressure, and and then compare a traverse to the larger branch that was at a much higher velocity, and we had very similar readings. We didn't show a lot of duct leakage. We didn't show a lot of difference. So that confirmed that we were on the right path with this. So what are the conclusions on from this process of how do we do things? How do we solve it technically and just through the course of the project? How do you make these things work? So from the technical side, induction diffusers are much like chill beams, but without cooling and heating capacity. So if you've done a lot of chill beams, you probably already know this. You've got a methodology that works. That same thing can be applied to the air side. The same thing that you apply to the air side of chill beams applies to induction diffusers. Airflow measurements from induction diffusers should always be measured with the DP and the manufacturer's charts or CVs, whichever they provide. Low velocity traverses cannot be used to calibrate VAVs or balance induction diffusers. And the takeaway we got from that is we can't use, now we know that we should be distrusting those low velocity traverses and other applications too. Now, there's not a lot of times where we would need to do that on a VAV, but now we know that that's not an approach we should be implementing, and we've trained all our technicians on from what we learned on this project. And process-wise, one of the best things that I can say to everyone here is to engage the stakeholders. When you have a problem like this, if we had been afraid to have the conversation and been insular and talked to maybe only our client, and maybe he talked to his other tab guy in another state, and we all agreed among us that we'll just calculate correction factors. We would have balanced the entire project incorrectly. We would have probably had fan capacity issues. So many things would have been wrong, and that would have been all on us for not following the manufacturer's directions. But likewise, I don't necessarily say just always blanket, do what the manufacturer says, even if you don't understand it. There's value in working at something until you understand why it works. But because we, got out of what, you might think of as your comfort zone and engaged everyone involved from the owner down and said, look, we've never worked on this type of system before. We've done things similar, but there's things here that are not working well, and we want everyone's input on it by engaging all the stakeholders in a productive dialogue. And I will say that, everyone, handled this well. Everyone was cooperative. Everyone wanted to see this work. And, we were able to have productive dialogue because sometimes we're just talking and we don't feel like we get anything done. This was a case where, all the stakeholders were great. All of them did what they should do. And through that dialogue and support that we got from them, we were able to get to the point where not only did we balance it correctly, but we understood why it's correct. And hopefully we're being able to share some of that with all of you and help you avoid some of these roadblocks that we experienced early in this project. So that concludes my presentation, and I'll take any questions.
Okay, thank you very much, Todd. I'm gonna kick us off here. First question is, what is the discharge air temperature in the room? That was early on.
Yeah, so the discharge air temperature in the room is difficult to measure because you can't you can't get a place near the diffuser where it's where it's really accurate. There's so much air movement there. But it's easy enough to calculate, because if your room temperature is 75 degrees and you're pushing 48 or 49 from the air handler, and your flow is roughly 50%, then you could measure that. But we did not directly measure that airflow. We did tinker with it a little bit. And if you're trying to measure with a sensor right there, there's just so much air movement. You can move it a little bit and it changes.
Thank you. And if anyone else has a question, feel free to submit them right now if you'd like. We have a couple more questions came in. One says, I might have missed it, but what is the discharge air temperature from AHU?
In this case, it was, I believe it was either 48 or 49 degrees. 49 degrees, because there was a 6 degree difference. So this one they were using 49, but in reading it, they do have applications where they'll go down to 45 and 46 degree discharge air with induction diffuser technology. So depends on the application, but here it was 49 degrees.
Right, thank you. And how did the manufacturer receive your findings, and did they consider sharing those issues with any future projects? Specifically noting why, I'm not sure if that's supposed to say pivot or pitot traverse may not be accurate. Interesting
Yes.
that they might not have that published.
Yeah, and we didn't get much feedback from the manufacturer after we got past that initial conversation, that meeting I described where everyone was there, and it was at least that representative, pretty much just said, you have to do it with the differential pressure drop, and that's it. That's the only thing that's acceptable. But back in their literature, they do give a little explanation about the boundary layer, and so they touch on it, but they don't get they don't get real deep into why, or how much, how far off it can be if you use different methods. So that primary meeting was really our only interaction with the manufacturer's rep, and in this case. But I mean, it was very, very pleasant. But pretty much that was their point, is this is what our literature says, this is what you have to do.
And I have two in here that have some numbers in it, if you don't mind popping up in the Q&A button so you can read along. This one's from Michael. Evergreen promotes a plus dash negative 2% reading of 0.001 in WC from 0.01 in to 10-inch WC. If you were to use this meter and come up with the same results, do you believe it could still be attributed to meter/measurement inaccuracy, or would further investigation have to be required?
Yeah, well, actually, we did use both Evergreen and Shortridge instruments on this project. I didn't mention that, but that's one of the one of the first things we thought was like, well, even though our equipment is calibrated, could it have been dropped? I mean, things happen. So our first, before we contacted anyone about the issue, any of the other stakeholders, we sent another technician to the project with not only another set of equipment, but the other brand, so that we could check that. And the readings were so similar. If you took readings from both technicians and put them in front of me, I wouldn't be able to pick one from the other. It was the same, in other words, in this case, the error was in the same range, regardless of which manufacturer we used for that.
Okay, thank you. And I'm looking at Blake now. Typical DP issues seen with DP chilled beams are with installations, you put example, leakage at connections, or disregard for leaving valve pressure, or like a pressure drop. And they put an example, you can get 0.7 inches WC of the device if valve is charging at 0.5 inches WC. Did this come into play with your experience at all?
Yeah, we didn't see that here, and the issue, I think, is that if I understand it correctly, is you're talking about if you don't have adequate supply pressure, then you're it's not going to work at the unit. And these devices use, because they don't have coils, the induction diffusers, they require quite a bit less pressure on the leaving side of the VAV than a typical chill beam will. and all of those were I don't think I included it in the chart, but we did measure that, and all of those were well above the minimum range. So that in particular, it's maybe another way that we can talk about how these devices are different from chill beams. But that particular issue didn't happen here, and because it's just my gut feel is because it's so much, the minimum pressure is lower than it is for chill beams because of the lack of coils. I don't think you're going to run into that, because if you have enough air to get the total airflow at the VAV, you're probably going to have enough pressure for these induction diffusers to function.
Great, thank you. Were the final DP measurements accurate given that 0.05 DP limit and low design velocities? How did direct DP measurements overcome low DP measurement inaccuracy?
Well, the low DPs were at the VAVs themselves. The low DPs, differential pressures that I described that were causing the accuracy problems, would have been with the traverse, whereas the higher DPs were at the devices. But let me flip and just grab that chart so I can say. But if you go back to the submittal on these devices for the airflow ranges that they were supposed to provide primary air for, the lowest DP at the induction diffuser was 0.09, and the highest was about 0.296. So all of those were well above the minimum DP by either in the Shortridge or Evergreen literature. So that's one of the reasons that they're more accurate than that traverse that we were initially trying, is because the differential pressure through the induction diffuser, across the induction diffuser to the open space itself, is much higher, and it gets you into a range where the meter can read that accurately and consistently. Thank
you, Todd. I have 2 more questions for you. This one's from Randall. What is system static? What if AHU total CFM does not match VAV total in the final tab report?
Let's see. The system static on this, I believe, was about now. And again, this was a large project where the air handler served multiple floors, and some of the other floors weren't complete, so they were just capped. And the project is not complete yet. We're still have several floors to finish. But at the time, I think we were running around 1.25 to 1.3 system static pressure in order to get the to have enough pressure to operate the VAVs. So the second part of that question, what if the air handler total doesn't match the VAV total in the final tab report? Well, I mean, there's 2 reasons that could happen. One is because one or both of the readings is an error. But so we did try this on smaller branches, where once we had a number of VAVs calibrated using the correct method, we opened those up and said, okay, if we traverse one VAV, we're down at 500, 600 feet per minute. But if we go back and traverse a branch, can we get 21 VAVs that we've balanced and find a branch total where the airflow rates or the airflow velocity is above, say, 12 or 1300. We traversed those and they matched very closely. So we're confident in that. Now, in the end, a lot of times we don't even show VAV total in an air handler sheet because of diversity. Because if you have a 10,000 CFM air handler, but there's 12,000 CFM of connected load, they often, they won't match by definition because they're not simultaneous readings. I'm not sure which question you're answering, or asking, but hopefully I answered at least one of them correctly.
Thank you. And final question for today. Did the manufacturer provide you with any information on how their lab tests were conducted? And they put some examples, sizing of the duct runs or velocities measured?
Yeah, they did not. We didn't see anything from them other than what was in the submittal.
Okay, that is it for questions today. Todd, thank you so much for joining us on AABC Tab Talk.
Glad to do it.
Okay, do you mind advancing your slide for me?
No.
I want to end this out by thanking Evergreen Telemetry for supporting this webinar and AABC, as well as once again to Todd for lending us his time today. So if you enjoyed this session, we do have another coming up on ASHRAE standard 62.1 and the recent changes that may impact you. And that is with Daryl from Ebtron. So we hope to see you August 17th, 2 p.m., same time. Looking forward to it. And everyone stay cool and enjoy the rest of your day.
Thank you.
Thank you all.